All right, we were continuing in we were talking about in our last class section 9.6. Now section 9.6 deals with the functions and surfaces. So we are considering functions of two variables, a function of x and y, and that function of x and y we set equal to z. So now you have three coordinates. You have an x, a y, and a function value. That's a z coordinate. And because of that, if we want to graph a function of x and y, it is a surface in three-dimensional space. And the points on the surface consist of three coordinates, x, y, and the x coordinate, the y coordinate, and then the z coordinate, which is the function of x and y. So this is the idea behind graphing a function of two variables. And they have some nice examples here in the book. They have some nice examples. We did the example 4, but if we look at example 5, they say, okay, sketch the graph of the function f of xy equals x squared. Now in two-dimensional space, f of x equals x squared is a parabola. But if you have a function of x and y and it equals x squared, that's going to be a surface. That's going to be a surface. And what would that surface look like? Well, it's going to be what's called a parabolic cylinder. Let me show you a little picture here. This is what the function looks like. It's a parabolic cylinder. Now, what's going on with that? Why does that surface look that way? Well, let me go to the whiteboard and give you a little guidance on this. Go to the whiteboard here. And let's see here. We'll change our font to 3-point. That's fine. So f of xy equals x squared. That means z equals x squared. And if you have z equals x squared, you could think of that as x squared plus 0 times y. So it means that the y, whatever the y value is, it doesn't change. Well, it doesn't really make a change, so to speak. So, like for instance, maybe I can try to do this here. What I'm doing is I'm going to draw our x, y, and z axes. And actually, I'll have to maybe do this as well. So I'm looking at example 5. It's in the ebook, and I'm just clarifying it a little bit. Now, let's say that y was equal to 0 and z was equal to x squared. If y equals 0, that's going to put us right here. And z equals x squared would be this parabola. So this is, again, y equals 0, z equals x squared. Every point on that parabola, okay, the y coordinate equals 0, and z equals x squared is a parabola in the xz plane. But let's say you had y equals 3 and z equals x squared. Okay, and I'll tell you what, let me pick a little point here. Just to, let's say this point is this point right here. Let's say that is equal to 1, 0, and 1. Okay, because 1 squared is 1. So, yep, that point's on that parabola. Now, if we have, so that's one curve. That's also called what we call a trace. It's what's called a vertical trace. Now, if we look at the curve y equals 3 and z equals x squared, okay, and maybe I'll just, put that there. Here's 3. Here's 3, say. If y equals 3 and z equals x squared, then I've got to be a little careful how I draw it. We're going to get another parabola. And this point here would have coordinates 1, 3, and 1. See how that worked? This is the curve y equals 3 and z equals x squared. So all you need to have happen is to graph this surface is that so long as z equals x squared, then any point that satisfies that, such as this point and this point, that point is on the surface. So essentially, you can take the parabola centered there at the in the xc plane and move it up and down the y-axis. And what that's going to trace out here is going to be what they call a parabolic cylinder. Now in the book, I go back to the example 5, that's what's going to get traced out. You see that? Take the parabola z equals x squared, that's a parabola in the xz plane, and move it up and down, move that along the y-axis, and you're going to trace that out. You're going to trace a parabolic cylinder out. Are there any questions on that? Is anybody uncomfortable? All right. You're good, Narina? All right. Who's feeling good so far? Give me a thumbs up. Narina's feeling good. Yeva, Simon. Okay. Okay. Wonderful. Angela, Shifa, Samuel, Alexander. Good, good. Well, all right. Well, let's look at another example. Let's look at another example here. They say, okay, in this example 6, use traces to sketch the graph of this function. F of xy equals 4x squared plus y squared. Okay. Now, I'm going to go to the whiteboard again. And this example 6, I'm going to write here. Okay, I'm going to write f of x, y equals 4x squared plus y squared. And remember, f of x, y is equal to z. So how would we graph this? How would we graph this? Well, so let's say that z equals 0. If z equals 0, then we have 0 equals 4x squared plus y squared. And so what does this imply about x and y? What would x have to equal? What would y have to equal? What are the only values of x and y that satisfy z equals 4x squared plus y squared? That's right, Logan. Both x and y have to be 0. Both x and y have to be 0. So x would be 0 and y would be 0. And so that means this, whatever this surface is, okay, it, in terms of a picture here, has to start at the origin. Okay, because the origin has coordinate 0, 0, 0. Now let me ask you, does this surface go upward or downward? This surface here, z equals 4x squared plus y squared. Surface goes upward. That's right, Alberto. It has to, because, very good, because x squared and y squared is positive. So let's say you wanted to say set z equal to 1. Well, if z equals 1, then 1 is 4x squared plus y squared. And that means that 1 is equal to x squared over a fourth plus y squared over 1. Now, why am I doing that? Because 1 equals 4x squared plus y squared. What does that trace out? It's not a circle. It's not a circle. A circle would have to be 1 equals x squared plus y squared. You'd have to have the same coefficients in front of x squared and y squared. But when the coefficients differ, what is this here? You remember? That's right, Norina. That's right, Logan, Lexi, and Simon. Very good. This is an ellipse. And it's an ellipse. If you remember correctly, you look below the x squared and the y squared, and that determines your intercepts. So the x-intercepts, that's when y is 0. That's going to be plus or minus a half and 0. And the y-intercepts are when x equals 0. So you're going to have 0 plus or minus 1. But the point is, if you think here of of the z-axis, okay, there's the z-axis, and you think of when z is 1, well, you're going to have an ellipse there. You're going to have an ellipse. And it's going to be wider in the y direction than in the x direction. Okay, and by the way, this is what's known as a horizontal trace. A horizontal trace. Horizontal traces are like we can. So it's difficult to graph in three-dimensional space, but if we take our function and set it equal to certain values, we can figure out what basically so like at the origin, we just have 1 point. When z equals 1, we have an ellipse. See, by letting the z value take on different values, like for this problem, we determine at z equals 1 what the surface looks like. And incidentally, if you were at z equals 2, what do you think would be there? If you set or let's say, tell you what, let's say z equals 4. Let's say you set z equal to 4, and so 4 equals 4x squared plus y squared. Well then 1 would equal x squared over 1x squared plus y squared over 4. If you divide both sides of this equation by 4, you'll get 1 equals x squared over 1 plus y squared over 4. That's going to be what? That's going to be, well, 1 would be x squared over 1 plus y squared over 4. That's going to be yet another ellipse, right? That's going to be another ellipse. And the x-intercepts are going to be plus or minus 1, and the y-intercepts are going to be plus or minus 2 for that. Okay, so maybe I'll just put that in down here. X-intercepts plus or minus 1, 0. And y-intercepts 0 plus or minus 2. So that's going to be then a wider ellipse here. And you see the idea. I'm sorry, my graph's not perfect, but the point is, if you connect everything, if you connect all these ellipses up, you're going to get a picture that looks like this. And this is what's known as an elliptical paraboloid. An elliptical paraboloid. Okay, so this is all in the recording. But are there any questions about? See, we have to get we're trying to graph something we're trying to graph a surface. So we have to wrap our heads around how we're going to do it. One nice way to do it is to set different values for the z, and then for each of those values of z, see what the surface looks like, at that value. And so this surface, by looking at different z values, it's like we're stacking up a bunch of ellipses on top of each other, and it traces out a bowl. All right. And by the way, I think I don't have this spelled right. Oh my goodness. It's called a paraboloid. I didn't spell it right. Let's see, forgive me. Yeah. One moment, we'll get it. Paraboloid. Yeah, paraboloid. Yeah, that's right. Okay, good. Okay. So yeah. And if we go back to the book here, There it is. And in this case, we used horizontal traces. So basically, think of this taking horizontal cuts of the surface. Every horizontal cut is an ellipse. You stack the ellipses on top of each other, you're going to trace out a bowl. Now, if you were to look at vertical traces are when you set x or y equal to a constant. So, like the previous problem we looked at, we had set well, I want to say this the right way. We had set different y values to be constants, and we got vertical traces. Okay, so you see, and here in Figure 6, you see how there's in the picture horizontal cuts and vertical cuts. So basically, you can figure out what a surface looks like that way, and sometimes you can have even more complicated surfaces. Like here they want you to sketch the graph of what's called a hyperbolic paraboloid. And for this, I'm not going to go into great detail on this, but this, in order to graph it, they need to look at traces in the horizontal traces and the vertical traces. Okay, and basically, if you put all this information together, now we can use MATLAB to graph this surface here. But if you were to do it using traces, which is kind of what I had to do back when I took calculus, when I took multivariable calculus, you put the traces together, and you're going to graph out a hyperbolic paraboloid. Okay, so that's another type of common surface. Now, I'll show you something here. I'll show you something. There are very sort of common surfaces that are that we use fairly often, like in homework problems and stuff. And these surfaces, let me just see if I can, yeah, there's a table here, table 2, that has graphs of quadric surfaces. Okay, and let's see, can I make that a little bigger? Let's see, maybe I can enlarge view. Yeah, so see, like an ellipsoid, like a football, has that equation that you see over here. In other words, and they forgot the equals 1, by the way, there's a typo. An ellipsoid has the general equation x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. That's an ellipsoid. Okay, that traces out that. An elliptic paraboloid, like the one we just saw, has a form that you see here. Now, hold on. Let me just check one thing. There's something I'm not. Okay, hold on. This is something I'm not particularly happy with here. They have some typos. They have some typos in this table. They have some typos, I'll tell you. That's sort of odd. I'm not used to seeing that. Let me bring just the original thing back. Hold on. One moment. Yeah, so these surfaces, there are like traditional surfaces that are used in multivariable calculus, like a cone. That's the cone surface. Okay, and it would that would fit the form z squared over c squared equals x squared over a squared plus y squared over b squared. And we already talked about the ellipsoid. And then they're about in table 2 in section 9.6, there are about 6 fairly common surfaces that we well, at least three of them we're going to encounter fairly frequently. But in a way, using the like traces to help you graph a surface, it's a little bit dated, the idea. I mean, I'm not saying it's bad. It's a good idea because it helps you feel comfortable with what like a simple surface, how to do a simple surface, how to graph it. But of course, the problem is that what happens if you have a more complicated surface? So like, for instance, if I go up a little bit here, let's see, I just got to find them, class. Yeah, see here in figure 10, look at those surfaces. And the equations for the surfaces are below. So those surfaces were not done. You can see they're more complex than the simple surfaces that the two that we looked at, the parabolic cylinder and the elliptical paraboloid. These surfaces are more complicated. But like if we were to look at the first one, for instance, and just give me one moment here. One moment, class. Okay, what I want to do, let's look at this figure 10. Okay, this surface. It looks like two hills across from each other. So the equation for that is hold on. Get the book a little closer so I can see it. Here's the equation for that figure 10, part A. Try to write this properly. And incidentally, I can write the equation like this, right? I'm going to do it right. Okay. So you have here two functions. Okay, here's the first function, and you're multiplying it by this second exponential function. So what does the first function do? The first function, as x goes to infinity and y goes to infinity, the first function Does it grow or does it decrease? This x squared plus 3y squared. What does that function do as x gets large and y gets large? It grows, clearly. X squared, right, Norina, very good. This first function grows. Now let's look at the second function. As x goes to infinity and y goes to infinity, that we could actually say as we move away from the origin, okay? That as we move away from the origin, if we're moving away from the origin, unlike in the xy plane, x and y are getting, well, I want to be careful here. Maybe to be more clear, I should have plus or minus, just to be. So as x gets large, like for the first function, as x gets large, and y get large, whether it's positive or negative getting large, because you have the squared terms there, that first part of the function is going to be growing. Now the second part of the function is an exponential function, e to the negative x squared plus y squared. So we know x squared plus y squared grows as x and y move away from the origin. But this second function is e to the power negative x squared plus y squared. So what would this second function do as x and y get large? What does it have to do? Does it grow or does it decrease? What do you think? If you have e to the negative infinity, that's 1 over e to the positive infinity, right? So that's right, Norita. So this decreases. So you have two functions here. You have two functions. As you move away from the origin, the first function is increasing, and you're multiplying it by a second function that's decreasing. It's like an arm wrestling contest. Well, you got two things acting opposite. It's like an indeterminate form. How many remember L'Hopital's rule? This is like this is like, what is this? This is like, as x gets large, this is like infinity times 0, right? That's an indeterminate form. Good, good. But the question is, what dominates? The exponential function grows, it decreases to 0. The first function, x squared plus 3y squared, increases to infinity. Which function's going to go more quickly? Will the first function grow to infinity faster than the second function, the exponential function decreases to 0, or will it be reversed? Which function, or will the second function, the exponential function, decrease to 0 more quickly than the first function goes to infinity? Who's going to win? You have a 50-50 chance. Alberto thinks the first. And I don't want to get too technical, but it turns out that the exponential function, the e to the negative quantity x squared plus y squared, that's gonna approach 0 more quickly than the first function. And if you remember L'Hopital's rule, I don't know if you let's see here. Let me just try this real quick here. And then we're going to go back to the example. This might, if you have the limit of, as x goes to infinity, of x times e to the negative x. Okay, this is like 0. No, this is like infinity times 0. It's an indeterminate form. X goes to infinity, but e to the negative x goes to 0, right? E to the negative x goes to 0. So L'Hopital's rule, remember what you do. You write it then as a ratio. And now both x and e to the x go to infinity. So you can use L'Hopital's rule on it. So L'Hopital's rule says take the derivative of the top and bottom. And now it's very clear that this limit's gonna go to 0. Okay, so Alberto, do you see that? This is just the same kind of Alberto was the brave. He ventured an answer. So okay. So this explains then. All right. Excellent. This explains then why. I don't want to. Let's see here. Sorry. Let me just. We don't need that. I just want to see this here. This explains why figure 10a, as the surface, as we move out from the origin, the surface gets flat because the value of the values of the function approach 0 as you move out from the surface. But even with that, even with sort of basic fundamentals, we might be able to determine that the surface, goes to, approaches 0, flattens out as you move away from the origin for this figure 10a, this first surface. But what about the two humps there? How would you get those? So this is a clearly a situation where we need to use MATLAB to help us. And for your first exam, you could have a problem where you're given surfaces like this, and you have to match the surface with the correct equation. And so, you would type the equation in MATLAB and graph the surface. So I want to do that for this first surface here. Okay, so now where do we go? To find that? Okay, well, let me show you here. So we go into Blackboard. Okay, and there's a link called MATLAB Programs. Can everybody see the link there? Give me a thumbs up if you see it on the left, MATLAB Programs. Okay, IB sees it. Wonderful. Simon, Angela, Narina see it. All right, and I'd like you to follow along with me. So I'm going to click on the MATLAB Programs. And then this module contains MATLAB programs that'll help you. So click on MATLAB programs, and now there is a link. There is a link right here. This MATLAB program will help you draw surfaces when you have functions of x and y. So click on the MATLAB program, and it should bring up what's called an M file. Okay, it should bring up an M file, and it should open up, like if you have MATLAB installed on your computer, and you want to have it installed on the computer you're taking the exam on, right? It should bring up if you just click on the link, it will bring up the MATLAB program and open up MATLAB at the same time. So what you'll see is let me just see here. You should see this. So try it. Now, you might, how many of you, how many of you are trying it now? I want you to try it. And if you have MATLAB installed, is it bringing like exactly what you see here up? It might look a little different, but are you seeing the program? So you have to have MATLAB installed to bring up the, if you click on the program, it might bring up like what's called a text file. But in order to bring up the you have to have MATLAB installed to get this to show. So, all right, so Lexi has to install MATLAB. Okay, Shifa says he has MATLAB installed and it doesn't bring it up. Okay, hang on. I think I know. Okay, I think I know. All right, I think I know what I'm doing wrong. So take that back. What I said, I forgot. This is different than the home computer. All right. So what I'm going to do is let me just open up the program. Okay, then let's do this. Hold on here. Where is it? It's just give me a moment here. Okay, one moment here. Yeah, it should open the program on your computer. So what I'm trying to do is show you what I have on mine. Let's see here. I just gotta. I see it on mine. Okay, hang on, one moment. Okay, hold on here. Let me bring it up on the screen what you should see here, but I have to. So again, this is if I were in the classroom, I would this would come up just fine, and you would see it on the thing. But here, we're doing this in Blackboard, so it's a little different, but it's okay. Let me just bring it up here. I called it ADD, the program. Just gave it a crazy name. All right. Okay, so let me ask you, when you click on the link, is this what you're seeing? Is this what you're seeing? This is what you should see. All right, Aaron's seeing that. Angela's seeing that. Norina, Yeva. Okay, that's great. That's good. That's fine. And what you can do is you can copy this text here. You can this is MATLAB code that's going to run a program. You can copy the text, and then okay, you can. I'm gonna do it like real here. So copy the text, okay, and then go into MATLAB, okay, and you should see, MATLAB might look like this. Okay, there's what's called a command line. Yes, so Angela says you have to add the symbolic, what's it called, Angela? The symbolic math add-on. Yeah, so when you install MATLAB, it gives you like the standard installation, but you have to install what's called the symbolic math add-on in order for this to work. So it's no big deal. You just open up MATLAB and you get it installed. Not a big deal. So now what I'm going to do is, okay, hold on here. Let me go into MATLAB. I'm going to click on something called New Script. And then I'm going to paste this in. I'm going to paste the code in. Now, whenever you run code, MATLAB code, you want to put it in what's called a new script, because when it's in the script editor, there is a feature on the right that tells you if there's a problem. Now, right now, all I have are warnings, okay, and it comments that Easy Surf is not like this code. This code is a little bit older, but I like the code because so far it works and it's very descriptive. But it mentions that there's another command called fsurf that you can use to graph the surface. But let's just stick with the Easy Surf for now. Okay, so the way MATLAB works is you have to, every time you have an operation that you like multiply, add, subtract, divide, you need to put it in. So you see there the times there between the two functions. You like on a TI calculator, you could just use like parentheses or something, but here you need to have the times symbol. Okay, and incidentally, if there's ever a symbol that you don't know, like MATLAB. So obviously in the homework, you're going to be given for section 9.6, you're going to be given a variety of functions that you're going to be coding into MATLAB, and you can use this standard program as like a reference. The part that you're going to be changing is what the function f is. What the function f is. You'll be changing that. But you'll keep the sims x and y. That means symbolic variables. That's why you have to add the symbolic toolbox in your installation. And then the Easy Surf command, well, this Easy Surf says, okay, take the function, graph the surface represented by this function, and the x and y, the limits on the x-axis are from -3 to 3, and the limits on the y-axis are also from -3 to 3. Okay, that's what that means. Now, what I'm going to do is I'm going to take the code. Here's how you run it. One way to run it: you copy the code. Oh, I'll mention too. You notice on the right here that it mentions about warnings, but there's no red. If there's something red, that means the program's not going to run. So if I were, for instance, to like for exponential function, or let's say I took out this symbol here, the times, I put it out. See that? See that how it goes red? That means that program's not going to run. So it's always good to take your MATLAB code and paste it directly into the script the script editor, so that if there's error in the code, you're alerted to it. Now, it's not perfect, but it's very helpful, very helpful. And if we go to the thing here, see it says here invalid syntax. So I'm going to go ahead and put the times back in here, and now you see I'm back to yellow. I'm back to yellow. And if it were yellow, if it's yellow or green, it should. Oh wait, hold on. What happened? Did my MATLAB go off here? Let me bring it back. It just went off, right? Just went off, right? Hold on. Okay, good. This is why I'm constantly checking. It's like Willy Wonka and the Chocolate Factory. You got to be ready for all kinds of surprises, Now I got to find where the doggone MATLAB is. Hold on, where is it? Hold on here. Just give me a moment. I had it. Oh, it's down here at the bottom. No. Here it is. Okay, so, all right. So if it's yellow or green, on the right there, you know that the program should run. And how do you run it? I copy it all. And on the left, there's a command window. I paste it right there on the command window. I do a paste. Okay, I do a paste. And then I hit enter. And it should graph the surface. And the surface, let's see, I have to open up a new window to show you the surface. How many of you have something like this? Okay, Angela has that. Arian has that. Okay, wonderful, wonderful. Now, I will tell you that in your homework, you're going to be presented with different equations, different functions, and you have to match the function with the correct surface. You don't necessarily need MATLAB to do that. You can just look at the function itself and try to figure out, certain properties. Like we figured out that this surface, as you move away from the origin, it has to be flat. Well, that was helpful, right? That was helpful. So, but I think MATLAB will be helpful for you. And so I encourage you to get it installed, maybe even before class is over here. See if you can run this code and get this picture. Okay. Now I'll mention something else here. We're almost done, but I'll mention something else while I'm at it. Okay. So you see, in MATLAB, there's a command called CLC. That will clear the command window. Sometimes the command window gets cluttered. Okay, maybe you want the command window to be a little longer, right? Okay, and there are ways, like in terms of viewing, you can have like a top-bottom situation, but let me just stick with what I had here. Hold on, let me just, I didn't really want to do that, but there we go. Okay, so I have it on none, and I got my command window and my script editor. So the command window usually, by default, when you open up MATLAB, the command window is always there, and then to get the script editor, you have to go up and, like to home here and click new script. Right? But sometimes you might have variables that you don't want in MATLAB anymore, and there's another command called clear vars. That clears old variables out. Okay, just keep those in mind. Now sometimes, hold on, did it go, did it leave? Did MATLAB go away here again? Hold on, let's get it back. Hold on, class, give me a moment. Yeah, well, that's why I'm always checking. I'm always checking. You let me know if that MATLAB's not shown, okay? Do me a favor, let me know. All right, I'm gonna open my MATLAB again here. I'm gonna open it fresh. I have to figure out what that's about. Give me a moment. We're almost done here. Okay, so there again is the MATLAB. Okay, and let me just see here. Let's give me a moment. Okay, there's my code. Now, sometimes what happens is like maybe there's a function that you need to type in your code, and you don't know how to type what it is in MATLAB. Well, if you go to the little command window here and click on the little thing below, you can browse, and it brings up a help menu. So, like for instance, let's say square root. Square root. You want to know how to type in a square root. Okay, well, hold on. I didn't type that right. Hold on. Square root. Ah, look, see? SQRT. So I click on SQRT, and it brings it up. But let me go back here. Hold on. I want to look at that. Yeah, so you see it, well, again, I'm just saying you have to click then on the square root. But pretty much any function that you encounter in your homework, if you don't know how to type it in MATLAB, you can learn how to type it by using the command line help. The command line help. Okay, does that make sense? And again, the command line help, you just click above that or below the little function symbol, and then it's very thorough. Okay, so that's our introduction to MATLAB, and that's really designed to help you with a particular problem in section 9.6, where you have to match some surfaces with some functions. Are there any questions? Any questions? Who's feeling reasonably good? I always like to see who's feeling reasonably good. Okay, Matthew is, Angela is, Yeva, Alberto. Okay, ours feeling good, still trying to download, wonderful. Shifa, Logan, good. All right, so what I'd like you to do, what I'm gonna do is we're done with section 9.6 now. We're gonna take a little break, and I'm actually gonna give you, about 20 minutes here, okay, this break, because I want you to use this break to get MATLAB installed on your computer and get that program to run. Okay, get that program to run successfully. That would be good. That would be good. Okay. All right. So let me go ahead and stop the recording.